Okay, well, we're here in the lab. I have something that I want to do. Um, in the review for electronics, we start with the atomic theory, and we talk about diodes, Zener diodes, and, um, and then we move right into rectifier circuits, and we do a review on paper, some rectifier circuits, single phase, three types actually, the single phase half-wave rectifier, the single phase bridge rectifier, and the single phase center tap rectifier. Okay, and we actually look at the three of them in our review. And a little later on, we are going to do some three-phase rectifier labs. But what I wanted to do is I wanted specifically to address the single phase rectifier circuits, and they're not hard to hook up. So what I've done is I've got them done here, and we're going to go through this clip, and I'm going to show you the values that appear in single phase rectifier circuits. So I'm going to start with the single phase half wave rectifier, which requires actually only one diode. Now I'm going to show you what I've done. I'm going to get a pen here. Okay, here we go. So see if I can get this done properly. Up behind me up here, I have 240 volts. Now what I've done, you can't quite see it. It is a three-phase supply, but I've only tied onto two lines. So, and if you look carefully right behind me here, you only see two wires coming down. And that's because the two wires are all I need. It's a single phase that hook onto that transformer. And as you can see, I've got nothing connected to the other transformers. And so I'm only using the one transformer. So this really gives me a single phase source. Now, what I've done is I've hooked the top of the transformer up parallel 240. And I've hooked the bottom up also in parallel. So I have a 120 volt single phase source. And I've tied that to A and the neutral, so the red and white bus bars. And now let's go ahead and take a look down. I'm going to show you the actual rectifier, what I've done. So I have some meters here I'm going to show you in just a moment. But basically I've brought from A line, I've brought this conductor right in. I only have one diode, so it comes through this diode, through the fuse. From here, this is going to go through the ammeter, which I have right here, from the ammeter over to the load. Now, make a note of this, okay? The load is two 30 ohm resistors in parallel, so it's actually a 15 ohm load, 15 ohms. And so I've made it a little lower because the voltage is not too high and I want to make the current so it's measurable. So single phase half wave rectifier, and let's look at the voltage that we're applying to the circuit, okay? This is the voltage, 124.6 volts. That is the single phase voltage, line voltage that we're applying to the rectifier. Now, we know that for this rectifier, the form factor is 0.45, E line times 0.45. And so if you do grab your calculator, 0.45, 120 times 0.45 is about the 54 volts, roughly in that range. Okay, so there's your 120 times 0.45. That's the DC voltage, 53.9 volts. Now, if you take your calculator and you go 53.9 volts and you divide it by 15 ohms, you should be relatively close to this 3.52 amps, 3.51, 3.52 amps. This is the DC load current. Now, something that is a question that comes up from time to time, and it is, how do we calculate load power in a single phase half wave rectifier? And because the rectifier is only half time, and when I say half time, maybe it would be handy for me to show you the scope. Just a second. Now, if you can see the scope there, I'm going to freeze that image because it's a little flaky. Look at that. Now you can see, I'm trying to stop it where you can see, there you can see. Now, you can see one whole cycle there. If you see that alternation on top, you've got one alternation where, and this is the load voltage, okay? You've got the complete positive alternation and then a flat line, which represents the negative alternation. So 0 volts during that entire negative alternation. And so what happens is, this is why we only have 54 volts. It's because we're missing an entire ripple. We only have one ripple. Our ripple frequency here is 60 hertz. It's actually equal to the supply frequency. So, you'll go, okay, that's why the voltage is actually as low as it is. Now, what is the power in this circuit? Now, we just looked at the scope and you see that this is a half-time thing. We're only really getting values half of the time. And so you can't really take 53.9 volts times 3.51 amps, because if you do that, and I'm just going to run this right now, 53.9 volts times 3.51 amps, that comes up to a value of 189 watts. Now, that's not very much power, and in fact, it's not the correct amount of power. What you need to do with these is you need to use line values. Now, you got a couple of options. We know the size of the load is 15 ohms. We can go 124.6 volts, that's our line voltage, squared divided by 15, and that equals 1,035 watts. Now, if this wasn't a half-wave rectifier, that would actually be the power. But as it is, we have to now say, you know what? That would be the power if it was full-time, but it's only half-time. And so we divide by 2, and we get a value of about 517 watts. Okay, so I'm going to clear that, 517. Now, one of the interesting things about this is that the form factors that apply to voltage also apply to current. And so what I've done is I've done something that's very interesting to see, and I've taken a meter. We have a meter in the DC side, and that meter says 3.51 amps. Now, on the other side, just coming from the line, from the secondary line, I put an AC ammeter in, and look what it says, 4.31 amps. So 4.31 amps is the AC line current, 4.31 amps. So you go, does that make sense? 4.31 amps. Let's think about the line values for a moment. If you go and you take the line voltage of 125 volts and you divide it by 15 ohms, you get 8.33 amps. And I go, this is kind of interesting. If I take 8.33 amps, but that AC current is only flowing half the time because the diode literally stops it and blocks it for half the time. So 8.33 amps AC on the line side. And if I divide that by 2, because it's half time, I get about 4.16 amps. And guess what? That's real close to what this meter is reading. And this meter is placed on the line side in the line, 4.31 amps. So very, very interesting. The AC ammeter actually tells the true story. And so there are two ways then that you can actually calculate power. You can use 124.8 volts of line voltage squared divided by 15 ohms. Or you can take 124.8 volts, that's the line voltage, and you can just simply multiply it by the actual measured line current, which is 4.31 amps. And that equals real close to that same value. This one comes out about 537, but it's just because the numbers have changed slightly while we've been talking. The voltage and the current will always fluctuate slightly. So the truth of the matter is, as long as you have the correct AC line current, you can use that times the voltage. But the best way, in my opinion, is probably taking E squared divided by R and actually then dividing it by 2 because it's only a half-time rectifier. Now, this rectifier is the simplest one, of course, very easy to put together. It only takes one diode. And so what I want to do is I want to shut this down. for a couple of minutes, and I'm going to do a little rewiring, and then I'm going to show you a full wave bridge rectifier. So we can go ahead and take a little stop right now. Okay, I've got that changed over. Now what I did was we're moving to the second type. This is a single phase full wave rectifier. It's called a bridge rectifier, uses 4 diodes. Let me just show you how they're hooked up. What you do is you bring from your line and you come in and you come to, you come with the line to a cathode and then the neutral to a cathode. You jumper the 2 anodes together, and this point becomes one of the points of the load. Then you do the opposite. You bring the line in to these 2 anodes, line and neutral into 2 anodes. You jumper the cathodes together, and this becomes the other end of the load. So the load literally is between those 2 points. And this provides you with a full wave output. Now, let me show you first of all what the scope looks like, what this waveform looks like. And it's kind of neat to look at it. You can see right away that now we have an actual full wave waveform there, and with both ripples. Now one cycle, of course, exactly 2 ripples long. The voltage that I have here is still about 125 volts, making the peak about 178 or something like that. Okay, so the peak is up there. You can see that the minimum voltage still 0 volts. So in other words, the ripple voltage here is actually the complete voltage from 0 to the peak. So the ripple voltage here about 173 or 174 volts. And so the line voltage that we're looking at is, I'll just show you this meter right away. This is the AC line voltage, 123.2 volts, 123.2 volts, line voltage. Now, let's take a look at the DC voltage. Now remember, the form factor for this rectifier is 0.9, E line times 0.9. So if you take that 123.3 multiplied by 0.9, you're looking at about, roughly speaking, that 106.6 volts, 107 volts. This is the DC average voltage that will appear across the load resistor, about 106, 107. Now, if you take that, I'm still using a 15 ohm resistor. So if you take that 107, you divide it by 15, you should be real close to this 6.93 amps DC. This is the DC load current that I'm showing you right now, DC load current. Okay, so let me just kind of conclude a little bit of summary for this circuit. This is the single phase full wave bridge. And just in order to, let's talk about power, calculating power in this circuit. And so what you want to do is, I still maintain the best way to do this is to use the line voltage and the resistor, very constant, pretty constant values. So in this case, we're looking at, I'm just seeing the voltmeter there, looks like 123 volts. So use 123 squared divided by 15 ohms, and then that value is actually the power in the circuit because it is full wave, so we don't have to divide by 2. So 123 squared divided by 15, and we're looking at right around 1,000 watts. So that's the actual output power of this full wave bridge rectifier. And now we just have one more rectifier that we're going to look at, and it's the center tap. Okay, so I'm gonna take a break here, and I'm going to rewire, and then we'll continue on. Okay, welcome back. Now what I've done is I've done a little bit of rewiring, and what I have set up behind me is actually the third, it's the third single phase rectifier circuit, and this is called a center tap. And let me just show you what I've done. You take a single phase transformer, and this is what I have right here, single phase transformer bank. I have 240 volts in parallel, so 240 volts on each of my primary coils. that gives me 120 and 120 on my secondary coils. Now, instead of having these in parallel and hooking them to the line, what I've done is actually hooked them in series. I brought the two ends down to line A and line B. So if I check across A and B, let me just show you the voltage across A and B, and you can see that it is about 247 volts. 247, I should be able to get that better. 247 volts. Okay, that is the single phase voltage across the entire secondary winding. Now, what I've done is I've taken the center of that winding and I placed it's a center, we call it a center tap, and that becomes the neutral. And so I took that to the neutral bar, and I'm going to move that up, and I'm going to look. Now we should have about half that voltage, and there we see it. There's that 124 voltage, roughly speaking, and that's my voltage from one end of the coil to the center. And if I moved my voltmeter to the other end, to B, you're going to see pretty much exactly the same voltage. So both halves of that secondary coil are even. Okay, so now what we're going to do is, let me just show you the wiring. We bring one line through one diode, the other line through the other diode, and we connect the other two ends together, and that becomes the beginning point of the DC load that goes out through my DC meter, through the 15 ohm load, and back to the neutral point, or the center point of that secondary transformer. So we call this a center tap transformer. Interesting thing is, let's take a look at actually the scope. I'm just going to bring it over. And let's take a look at what the scope shows for this one. Now I've got roughly speaking, and I'm just going to freeze this for a second. Look at that, full wave, just a full wave single phase output. So exactly the same as what the bridge gave me. Okay, there's going to be no difference in the values here of load voltage and essentially power, right? Power, current, things like that. So exactly the same waveform. I still have my minimum voltage is 0 volts, and my maximum voltage is 170. And everything in between there, we call it E-peak, but that's also ripple voltage, and you can see it there. Okay, so let's set this aside, and let's take a look at the meter that shows me load voltage. This is the DC load voltage. And you see that if I look at that there we go, there's a nice spot right there, 107.2 volts. Now, if you take 124, multiply it by 0.9, you should see that that's about your 107 volts there, okay? So that makes sense. Form factor, E line times 0.9 gives you the load voltage. And if you divide that voltage right there by 15 ohms, which I have in the connected load, you're going to see that you're going to come up with a number real close to this. And this, of course, is 6.97 amps. And your load current should be, that you calculate, should be reasonably close to that, okay? So there you see it. Now, for this one, we want to calculate power. We're going to use this pretty much exactly the same method that we used when we calculated power in the bridge full wave rectifier. So please just use your E line value, which at this point is 124 volts squared, divide it by your resistance, which for this load is 15 ohms. And seeing as it's a full wave, that's it, that's your power. The only one that you have to divide by 2 to come up with the power on is the single phase half wave with just one diode, the first one that we looked at in this clip. All right, so that's kind of a summary. This is a review summary of the single phase rectifiers, and I wanted to show it to you just to remind you very well of how the single phase were put together. And of course, the next thing is we're going to be doing some labs with 3-phase rectifiers, and so that'll be coming up fairly shortly. All right, thanks for watching.